Hello, everyone. First, I'd like to thank the organizers for inviting me to give this pre-recorded talk. What I'm going to be talking about today is a machine learning-based reconstruction for liquid argon time projection chamber. I was told by the organizers that the audience is quite varied, including Pheno and theory people. And so I'll start by giving a brief introduction and motivation for why this is important. So if we look at the oscillation neutrino experiment, what you typically have is a couple of ingredients. The first thing is you have a near and a far detector because you want to constrain the flux that is produced at your neutrino production point. And you also have a far detector where you measure the oscillated flux of neutrinos. And to measure an oscillation effect, so basically a change in the composition of the beam in terms of muon and electron neutrino, for instance, you need to be able to distinguish between the two different types of neutrinos that interacted in the detector. And you also want to be able to measure their energy accurately. What that means, if you look at the far detector, and the far detector is placed very far away from the production point of the beam, there's a couple of things that you need to achieve. The first thing is that the number of target count needs to be large, so the detector needs to be very big. You need to have exquisite electron versus muon neutrino separation power, and you need to have very good energy resolution. And so what detector fits the bill? Well, one of them is the liquid argon time projection chamber, which is why this talk is about this detector technology specifically. And it's also the detector technology of choice for Dune and the short baseline neutrino program. It is dense and it's cheap, so you can, buy about a kilogram of argon for about $1, and so you can make these detectors very large. It's relatively fast, so you can actually, operate these detectors at the frequency at which the neutrino beam will be pulsed. It gives you very precise tracking, so very detailed images essentially of what happened inside of the detector, and it also gives you very detailed calorimetry. The basic physics principle for this detector is if you have a neutrino interacting inside of the bulk argon, it will produce some charged particles. These charged particles will propagate inside of the detector and deposit some charge, and then an electric field will drift this charge towards the sensitive plane of the detector. The reason we like these detectors is if you think about an electron versus a muon neutrino interaction through charge current interaction, they will look quite different in this detector. And the reason is one will make an electron shower, which is what you see on the left-hand side, and one will make a muon track. And so if you visually look at these two objects or these two images, they look, strikingly different. The other thing that's nice about having precise calorimetry from this detector is that you can do energy reconstruction better than you would be able to in other detectors because you can use the straight calorimetry to do electromagnetic shower energy reconstruction, essentially. And you can also use this detailed chart information to distinguish between different particle types. So for instance, the amount of energy deposited per unit length give you information about which type of particle interacted. And then based on the precise range reconstruction for these tracks, you can reconstruct the energy of these individual particles. And so getting the energy of particle correct is something that's going to be a good proxy for reconstructing the neutrino energy. The issue is that the two images I just showed you are actually not the common images that we see in a liquid argon time projection chamber because the energies we operate the beam at and also the fact that argon is a relatively high Z nucleus mean that the type of interaction we see look more something like what I have on this slide. So there's a bunch of different things coming out of the vertex, and it's very difficult to tell by just looking at this image whether or not it's an electron neutrino or muon neutrino because there's a lot of shower activity, there's a lot of track activity, and distinguishing between what is a muon track versus other types of track and what is an electron shower versus other types of shower is going to be crucial. So the goal of reconstruction, which is essentially what I'm going to be talking about today, is to go from the raw image which comes out of the detector, which are these 2D projection of the image we get from the LArTPC, to a really high-level representation of what we want to do physics with. So we want to know where the neutrino vertex occurred. We want to know the list of particles that came out of this primary vertex and their respective energy. The issue has been is that using traditional reconstruction methods to approach this problem has not worked. So it's been something that's been in development at this point for over 10 years and been implemented for both Dune simulation, but also the SBN physics program. And what we've seen is it doesn't quite match the expectation. So the expectation is given what we can achieve by just hand scanning images, so just looking by hand at what we see in images and extracting information that way to what we can achieve with traditional algorithms. So here I give you a simple example where you're trying to select one EX event, so it's events coming from electron-neutrino interaction. What we can achieve by hand scanning in a simulation is something like 85% purity and 80% efficiency, but what we can do algorithmically with traditional methods is about 15% in efficiency for slightly lower purity. And so there's a real problem in that we will not achieve the physics program of these experiments if we don't address this reconstruction challenge. And so machine learning comes to the rescue because we're essentially dealing with images. This is what we're trying to reconstruct. And so it's a computer vision problem. And if you haven't been living under a rock for the past few years, you will have noticed that in computer vision problems, machine learning is the state of the art. And so how do we phrase the issue or the problem of liquid argon time projection chamber reconstruction in terms of a computer vision problem? The way we've done this is to hierarchically extract, useful information out of liquid argon time projection chamber image. What we start with is charge deposition inside of the detector. So you see an image as you would get from the detector on the left here. The first thing we want to do is to distinguish between different types of activity in the detector. So that would be mostly track versus electromagnetic activity. As we mentioned before, that's particularly crucial for doing muon versus electron neutrino reconstruction. We want to identify important point that would include the vertex, but also the endpoint of tracks, the start point of shower fragments, etc. We want to cluster the different particle into instances. So we want to distinguish between different tracks that occur in the detector. And we also want to aggregate different fragments that come from the same primary electromagnetic activity together. We also want to cluster particle into interactions. So it would be merging multiple particles into one interaction, neutrino interaction, from which we can infer the neutrino type, but also the neutrino energy. The data set that I'm going to use today is a generic data set of interaction inside of liquid argon. So it's not a specific detector. The reason for this is not an experimental talk. And so this is easier to show to the public. But this is very well representative of what we will see in a detector. The basic idea here, we don't use a neutrino generator. We just use what we call particle bombs. And so particle bombs are just a bunch of particles coming out of a common vertex. That's what you can see here at the tip of the red arrow. And then we overlay this with a bunch of different cosmic ray-like particles. So it's just going to be single particle individually distributed inside of the detector. The first task of the reconstruction, as I mentioned it before, is to do semantic segmentation. So at this point, we have a bunch of energy deposition in the detector. We don't know what that is. And we're trying to distinguish between different types of activity, which is what you see on the right. The 5 different types of activity we're typically interested in is to distinguish between track and showers. As I've mentioned before, that would be the red and the blue category. And then we have a few subclasses, which are smaller but important of electromagnetic activity. One is Michel decay, so this would be the green here, and they correspond to small electromagnetic shower happening when a muon decays in the detector. You have also electrons that are knocked on by tracks in the detector. These are the deltas. And then you also have spurious activity in the detector, which typically corresponds to small low energy photons interacting in the liquid argon. What we use to do this semantic segmentation is called a UNet. So I'm not going to go into great detail here because this is not a machine learning talk. But this is a very common architecture of a convolutional neural network used to do semantic segmentation. So classifying different deposition or points in the image into different categories. The specificities of the unit we use for liquid argon time projection chamber is that we use sparse convolution. So what that means is we only convolve onto active regions of the detector, which in the case of LArTPC is particularly crucial because the occupancy of liquid argon time projection chamber images is about 10 to the minus 4. So there's a lot of empty space. If you had to convolve on that, it would take a lot longer and also use a lot more memory. If you look at the performance for this semantic segmentation classification tasks, you can see that we achieve exquisite separation between electron and track activity above 99%. The confusion is something like 10 to the minus 3. So that's really a good start and a good basis for the rest of the reconstruction. The next step is to identify points of interest in the image. So that would be the start and end points of tracks and also the start point of shower fragment at this stage. We reuse the UNet that I just described. The only difference is we add a few convolutional neural network modules on top of it. And the goal of these is to essentially progressively extract regions of interest inside of the image at different level of resolution. So we start by producing a mask at the deepest layer of the UNet. So that would be the most compressed version of the image that we're putting in the neural network. And you can see that the predictions we're making at that point are really blocky and not really accurate. And in the next layer of the UNet decoder, what we do is we narrow down that region to a smaller area. And then if you keep doing this until you get to the highest resolution, you actually get a specific point prediction in the image, which is what you're seeing here. So you can see that there's a point now at the vertex of the particle bomb, and there's points at the endpoints of tracks, etc. What's really cool to see is if you look at the right-hand side histogram, is that the resolution we achieve is actually smaller than the pixel size in the detector. So we're actually able to nail the position of points of interest more accurately than you can by just picking a specific pixel. The other thing that's really cool is if you look at the blue histogram, you can see that within 5 centimeters of where we expect to see points, we have a predicted point. So the efficiency of recognizing a point of interest is about 99%. The next stage of the reconstruction is to do clustering. So we're trying to distinguish, different instances of particles at that point. And the first step of doing this clustering step is to break up the activity in the detector into different particle fragments, as we call them. So at this stage, we're trying to separate different tracks that touch from each other. And we're also trying to cluster electromagnetic activity fragments. So we're not trying to do, clustering of big electromagnetic showers just yet. What we use to do this is what we call graph spice, which is actually, again, a UNet. But there's a big difference is the way we interpret the information at the end of the UNet, which is to build a graph onto all of the set of points that we have inside of the image. We just use something like a KNN graph. So you're just connecting pixels to the direct neighbors, something like 5 neighbors for each pixel. And then you try to classify whether an edge should be on or off. If it's on, then these two pixels belong into the same instance. If the edge is off, then these two pixels should be separated into two different instances. What you see on this image is maybe a more pictorial version of explaining how this works. On the left-hand side would be the input edges. So each of these blue lines correspond to an edge in the graph that we start with. On the right-hand side, the black edges are the edges that the neural network have selected as being legitimate. So basically as connecting points that belong to the same instance. And so if you use connected component clustering, which is basically saying if you have two pixels that are connected by at least one edge, you put them in the same instance, then you can see that this is a way of extracting particle fragments, so separating these two track instances at the vertex. We run into an issue at this point of the RICO, which is that doing clustering for far-ranging interactions, so essentially if you have an electromagnetic shower, you have a bunch of fragments that seem disjoint in the image. And if you have a neutral particle propagating in the detector, you might have activity very far away from the primary vertex. That's very difficult to do with a CNN and with short-ranging connections. And so we need to change the representation of the data at that point. What we do is that we embed the fragments that we produced at the previous stage into nodes inside of a graph. So we now say that the node is not a single point in the image, but it's now a fragment that we've constructed at the previous stage of the reconstruction. We connect these different fragments together inside of a graph. And then we extract information both about the fragments and the edges by using what's called a graph neural network. I'm not going to go into great detail again, but the basic idea here is we have edge and node convolutions. So it's a way of aggregating information for the edges by combining information coming from the node that the edge connects, and for the nodes by aggregating information from the nodes that are connected to that node. And what we do at the end is very similar to what we did at the previous stage, which is to ask the neural network to tell us which of these nodes are connected together. So at this stage, it's asking whether the fragments should be put together into a particle instance. And we also can inquire about the node properties specifically, which I will talk about later. If we do this, then we start with the fragments that you see on the left, and what we get at the end is the 4 particle instances on the right. And so you can see that the fragment that make up electromagnetic showers now have been combined into singular particle instances, which is closer to what we want to get to for the neutrino interaction reconstruction. If you look at these metrics, it gives you an idea as to how well we do this job in terms of clustering efficiency and purity. You can ignore ARI for now, but efficiency is just a measure of completeness. So it's how much you're actually catching of the energy deposition into the instance as you should. And purity is essentially a measure of how much you're mixing instances together. So you want both of these numbers to be very close to 1 for not mixing particles together, but also aggregating all the energy that you expect to have for that specific particle. The next stage is we want to aggregate the particles into interactions. So now we have a list of particle instances we want to put together into an interaction to say this is one neutrino interaction. And so we can reuse this graph neural network that I just described. The basic idea here is that we put the particle instances inside of this GNN at this point instead of doing the fragments. And the predictions that we make is to ask whether or not these particles belong to the same interaction instead of belonging to the same particles. It's a very similar idea, and this is why we reuse the same architecture. If we do this, again, you can see that the efficiency and purity for doing this task of separating the activity into different interaction is exquisite at the 99.5% plus level for efficiency and purity. So that's really cool to see. The other thing we can do is we can inquire about instances inside of that graph. So doing particle identification, for instance, which is something that I discussed being crucial when you're trying to do muon versus electron neutrino reconstruction. And you can see here that the electron versus photon separation, which is this EM activity, is at the 90% plus level. And for the track, you can also very reliably distinguish between muon and protons with a bit more confusion with pion, which is something that we expect. And so if you put all of these pieces together at the end, then you get what's called SPINE, so scalable particle imaging with neural embeddings, which is a reconstruction package, which is, as you can see, entirely machine learning based and takes the input image that you get from the detector and at the end outputs something that's a really high level representation of what happened in your detector in terms of what neutrino interaction happened, their species, and their energy. This is actually a fairly big effort at this point. There's a lot of people on, 5 different experiments involved with developing this package. I'm just, giving them a shout out on this map as to all the people that have contributed to what I'm presenting today. Another thing I wanted to briefly mention is that this is really scalable. So it's machine learning algorithm. So it's very much optimized for GPUs acceleration. And so if you take run 2 of across, which corresponds to something like 6 months of data taking, you can reconstruct the entirety data set taken, the entirety of the data set taken by a big experiment like Icarus at SBN within a day with very modest resources, so something like 20 GPUs, which is something you get on a development cluster, and something that was an embarrassingly low amount of resources if you're talking about high power computing centers. I just want to briefly, give you a sense as to how well this works on actual physics cases. So I'm just going to take Icarus detector as an example. Icarus typically sees one neutrino interaction in one event, and there's a bunch of different cosmics overlays. So what we're trying to do essentially is pick out the neutrino interaction and reconstruct it correctly. There's a lot of different, physics target that we are looking into. So there's a long list here, which I'm not going to go into great detail. But the takeaway I want to highlight is if you look at the table at the bottom, I've taken 3 different reconstruction targets, so selecting muon neutrino, electron neutrino, and muon neutrino that produce a pi zero. You can see that in all cases, if you compare SPINE to other non-machine learning reconstruction paradigms, that both the efficiency and the purity of this selection have dramatically increased. And in particular, if you look at the electron neutrino selection, both the efficiency and purity have become actually very, very close to what a human can achieve by just hand scanning images. So that's really exciting to see. Here I'm just also showing an example if you're wondering about data versus simulation agreement, which is a frequent concern when you're looking at machine learning algorithm. You can see the data and simulation agree very well in these 2 specific cases that I picked up. Another thing that's interesting to think about is how much we can handle pileup with this method. And so the detector which will see the most pileup in the future will be the near detector of Dune, which will see 100 plus interaction per spill. So it's just a single pulse of the beam. And so you can see here, this looks like a really messy image on the left, and you're wondering how you're going to be able to separate the activity into different interaction. But it turns out that if we use the methods that I've highlighted earlier in this talk, this works really, really well. So you can see that the efficiency and purity are actually quite high at separating activity into different neutrino interactions. I also want to give a quick shout out to things that was not able to talk about in this talk. So I had really limited time, 20 minutes, a short amount of time. And so I did not talk about the Dune CVN, new graph, or the dedicated machine learning algorithm, but there's other activity in the field of LArTPC trying to use machine learning to achieve the physics goal of SBN and Dune. But I think what's also more interesting is that the next paradigm shift, I believe, will be the self-supervised point and image transformer, idea, which is very similar to how we train large language models these days, but applied to the field of LArTPCs. So, stay tuned for that and read the paper at the bottom of this slide if you're interested to find out more about this. So I'll just, at this point, I think I run out of time. So I'll just leave you with my conclusion slide and